Okay, so Science 8, this is the optics unit. So let's have a look at what we're looking at. So we're going to be studying what is light, what inventions use light, and what do these inventions reveal about the nature of light. And once again, thank you to Rebecca for sharing her notes and wisdom with me. Okay, so what is light? So light is a source of energy you can see. Light radiates or spreads out in all directions, and light is called radiant energy. It does not require matter to travel. It does alternating magnetic and electric fields. The farther away you get from light, the less intense it is. So the distance squared is, so if you're like twice as far away from the sun, the light is 4 times less. So light can be converted to any form or many forms of energy, including thermal, electrical, or chemical. The brightness or intensity of light indicates how much energy a surface will receive. And we know that all objects that emit light are called luminous. And we have natural sources like sun, stars, and fire. And then we have artificial uh, objects that emit light like candles and light bulbs. So there are different kinds of light sources. So the first one is incandescent. This is when an object is heated to such a high temperature that it emits visible light. It essentially glows. So that's the old, like over here, the old incandescent light bulb. And that's a filament in the light bulb. It's made of tungsten. Now these make great quality light, and they're very inexpensive to make. However, it wastes a lot of energy. Only 5% the of energy is changed to light, 95 is heat. I mean, it makes sense, but you have to heat this up until it glows. The fluorescent light source is more energy efficient and uses high energy. So electricity goes in, makes high energy UV, and that's absorbed by particles causing to emit light. So like a fluorescent light bulb, like the lights that are inside the school in many rooms right now. And here, this shows you the energy conversion. So gets absorbed by mercury particles, makes UV. The energy is absorbed by phosphor particles, and then visible light emits. And we talked about those purple lights on the way to Calgary. And what's happened there is the phosphor coating, for whatever reason, has fallen off, and that's why it's giving off the purple light. These are expensive. The chemicals inside are toxic, but they are pretty energy efficient. I think around 30 to 40% efficient. So that's way more than 5% for the incandescent light bulb. And we have phosphorescent sources. This is similar to fluorescent source, but the phosphorescent particles take longer to emit the light, and they continue to glow after the energy is removed. So these glow-in-the-dark toys, like these ones, are the classic example of those. And we have chemiluminescent source. This is where light is released from a chemical reaction, so like in glow sticks. We have bioluminescent sources. Bio means life, and so this results from chemical reactions inside living things. So jellyfish, fireflies, some fungus, and there you can see some examples of them. And then we have electroluminescent light. This is LED lights. And so electricity is passed through a semiconductor which emits the light. We did cost of lighting calculations. So electricity is measured in watts or kilowatts, and electrical devices are measured uh, using kilowatt hours. And the formula for calculating the cost for running an appliance is cost equals kilowatts times time times the price. The time has to be in hours, price is in dollars, kilowatts. And we did some calculations with it, right? How much does it cost to leave a 60-watt light bulb on for 10 hours? The electricity cost is, 10 cents a kilowatt hour. So you have to change the watts to kilowatts, and then you multiply them all together, right? So 1 mark for this, 1 mark for substitution, 1 mark for answer when we're doing the assignments. So 0.06 kilowatts times 10 hours times 10 cents means it's going to cost 6 cents for that. And we did some practice with this as well. And this example was not a very good example. And then we looked at the ray model of light. So you can represent light with basically a line, because light travels in straight lines from all directions from its source until it strikes something. Light can strike 3 types of material, and the ray diagrams show the path that light travels. Okay, so opaque material, what happens when light strikes it? No light is allowed to pass through. So here's some examples: wood, rocks, cardboard, and basically here is the light hitting an opaque surface, and you could see it could either get absorbed or a little bit reflects back, which is why you see it. Something that's translucent allows some light to pass through, although it's scattered. So frosted glass, tissue paper, wax paper, parchment paper that we used to make the cameras yesterday. And here you can see some is going through and some is bouncing, and it's going kind of all over the place. And then if it's transparent, all the light is allowed to pass through, transmit through. Clear plastic or glass, and here you can see the light rays are going all the way through, and these are ray models. There's a better picture of this in the textbook if you want to look at it. And then we filled this in, right, and looked at what light does as it goes through different kinds of material. And then topic 2 is reflection. Okay, and we made the pinhole camera the other day, and light passes through in a straight line. Reflection, we really didn't see a lot of reflection in that lab. That was more a lab about the ray model of light. Reflection is a process where light strikes a surface and bounces back off that surface. If you have a light surface, most of the light is reflected. If you have a dark surface, most of it is absorbed. We know this. On a hot, sunny day, you wear a white t-shirt or a light colored t-shirt. In the winter, most of our winter jackets are black because it will absorb energy. And we did talk about the fact that that creates a problem at nighttime. So at nighttime, you should wear a white winter jacket, and daytime, a black winter jacket. But how many of us have 2 winter jackets? And so there's the incident ray, there's the reflected ray, the ray that bounces off. And we have a normal, which will be in the next slide. There it is. And here is the angle in here of incidence, and here is the reflected angle. And we did comment on this picture. There is definitely something wrong because this picture does not. This angle and this angle need to be the same. Okay, and this one is a bit better. There's the angle of incidence, the angle between the normal. Normal is just, perpendicular to the surface. There's the angle of incidence. This in here will be the angle of reflection, and this should be the same as that one. There it is, the angle of reflection. And there you can see the angle goes in, the angle comes out. Sorry, the angle goes in, the angle comes out. There's your angle of incidence. There's your angle of reflection. There's your normal. There's your reflecting surface, and they are the same. Angle going in, angle coming out are the same. And the law of reflection says that light will always be reflected back at the same angle that it strikes it. I showed you how to use a protractor, so you have those skills in place. I don't know how to do a protractor on this program. And so there it is, once again, reflecting surface, angle of incidence, angle of reflection. We did a whole bunch of worksheets. We have a lab coming up soon. And that was just practice with angle of incidence. You need to draw the reflection. So in this case, the reflected angle, would come out. There's your angle of incidence. It would come out the same way. Freehand draw, that's horrible. But that would be your angle of reflection. Same thing here. There's your angle of incidence in here. And so it should bounce off this and come off at the same angle. Oh, it's a little bit better, but horrible. And there's your angle of reflection. And when light is reflected off an object onto a smooth, polished surface, an image can be formed. The image appears to be identical to the actual object in size and distance from the reflecting surface. The difference, though, is the image is reversed. An image is only formed if 2 reflected rays extend back and they meet. And then here you can see images and mirrors are also known as virtual images. Objects appear seem to be coming from behind the mirror. The image is also known as a lateral image because it is reversed. And so once again, there it is. So you're looking at this object, so the rays from it come here and bounce back. And what you see, though, is an image that looks like it's on the other side of the mirror. And then we'll be looking at curved mirrors. These are convex mirrors. They bulge out. They form images that are smaller and farther away than the actual objects. And that allows you to be able to see a larger area. And then there's concave mirrors that cave in. They form images that are larger and closer than the object. This is used to magnify images. And when light strikes a mostly smooth surface like a mirror, you can form an image, a reflection, and the light is reflected uniformly. However, when light strikes a rough surface, you can't form an image because like the reflected rays are going all over the place. Okay? And that's why it has to be smooth in order for it to reflect. In this case, well, it's still reflecting, but you can't get an image because the light rays are going all over the place. And when light strikes this paper, the white part reflects the light back to the eyes, so you see white. When you shine light on something that's black, it absorbs all of it, and therefore no light goes back, and that's why you see a spot that looks black, because no light is coming back to our eyes. And then refraction is in the next one. And then there'll be a quiz on topics 1 and 2.